Right. Good afternoon. Welcome to our Thursday afternoon colloquium. It's my distinct pleasure to introduce the speaker of the day, Dr. Nathan Carlie at Schott. He got his PhD at Clemson University in the area of solution-based preparation of optical quality chalconite glass, thin films, and inorganic polymer hybrids, and comparing their molecular structure to traditional PVD materials using Raman spectroscopy. And since he has been a scientist at Schott North America, where his work focuses on development of novel materials and manufacturing methods for optical industry, with a focus on laser and infrared applications. And this includes fundamental material research as well as internal and external application engineering. So with that introduction, I'll hand it over to Dr. Carlie. Thank you.
So just throw something at me if you need to. So I'm a glass guy primarily. I started in optics at Creel during my undergrad, but I moved over to glasses. I'm a chemist by training. But something that I've kind of felt lacking recently is strong interaction between optical designers and the people who make the optical materials. So I was hoping to kind of spark a little of that interaction here. And the other thing, the great thing about glasses is this idea of tailoring. So you have a crystal. The crystal has the properties it has. You're stuck. You can either use them or you can't, or you have to learn to live with them. But with a glass, you can tune things, change things, optimize them for whatever you need to do. And that's one of the big things in my job. But one of the really nice things that we like to get from people like you is, well, what's needed? What does optimized mean? And there's a lot of different definitions for that. So keep that in mind, because those sorts of questions I like to ask people, ask designers when I'm out there, and I get often answers that don't make a lot of sense, and then eventually people get thoughtful and actually come up with things that are interesting. So, be thoughtful about those kind of things. So particularly, my interest right now is in multispectral imaging. And the reason for that is because both image processing capability and the cost of the silicon chips that we use for all sorts of imaging are coming down so fast that you can really pack a lot of capability into a very small device. And I think this is a big and upcoming place for the future. From medical through environmental testing, looking at product quality. So you can see an apple there. You can see below that there's some silicon solar cells. You can see inside the chips themselves and how well they're going to perform from that. There's a lot of different places that this can apply, and I kind of have a vision in the not-too-distant future of having sort of an all-purpose camera. You take a picture, it collects tons and tons of data, and then later on, if you need to sort through that to find something interesting in it, be it maybe a chemical signature or whatever, it'll be there. And I don't think we're too far from it. But one of the things that's missing from there, I think, is while the technology in silicon chips has come a long way, the optical materials are basically the same as they've been for 50 years. So if we're going to see those applications flourish, we need new materials. And in particular, the direction that that's growing in is into the infrared. And I don't know how many of you are really familiar with infrared, so I wanted to go ahead and just bring that up in a general sense. So this is the atmospheric transmission. So you've got gases there, mostly water and CO2, that are your big problems. And so there's certain windows through which the atmosphere has very high transmission. And then there's other regions where it's very low because of those absorptions. So you've got near IR and shortwave IR, and all these things are sort of difficult to define. But generally speaking, in this sort of near the end of the visible out through about 2 microns, 2.5 microns for those. And that's primarily used for low light situations or doing some sort of analysis of things that aren't visibly transparent. And then mid-wave and long-wave infrared, and those are in the 3 to 5 and 8 to 12, 13, 14, depends on who you ask, microns. And those are primarily used for thermographic things, so looking at the temperature of an object. So that could be military, it could be non-military. There's lots of different potential applications out there. But at any rate, the issue with combining these applications is that now I'm not spanning, say, maybe 430 to 650 nanometers. I'm going all the way out to 14 microns, 10 times, maybe 15 times the span of wavelengths that a normal optical system would have to cover. So the engineering of that is extremely challenging compared to just your average optical design. So in order to accommodate that, and I've worked a lot with designers who have to kind of scratch their head and think about how am I going to pick materials that work, I've come up with a new glass map. And I wanted to kind of show you how that works, because if you're looking to choose an optical material, it's nice to have an easy tool. So traditionally, the way the glass map works is you've got this either index and Abbe number, or alternately Abbe number and partial dispersion, and you will find the location of several glasses on there. And if this is partial dispersion, what you're looking for is a horizontal line. Usually what you want to see on this one, which is index versus Abbe number, are materials up here. And of course, it's completely empty. And there's some nice physics reasons for that we're always pushing to get a little bit closer. There's a lot of things that you have to keep in mind when you're doing an optical design. So you've got to get rid of course, all the normal aberrations like coma, astigmatism, and so forth. You also have to get rid of chromatic aberrations, so that's due to dispersion or change of index with wavelength. And that's really where these multispectral applications start to suffer. And then in addition to that, there's also thermal effects, and that's often ignored in, or at least a much more secondary concern, in visible applications. But in infrared, it becomes hugely important because they're extremely sensitive to temperature, most infrared materials. So this is also an extremely big concern for infrared. And the problem is that this glass map that's traditionally defined at certain wavelengths in the visible is basically meaningless in the infrared. And in fact, depending on how you define these SWIR mid-wave bands, which ones you want to combine, you could have dozens of different glass maps to look through to try to figure out what combinations of materials are going to work for you. And that has proven to be fairly challenging for most folks. So instead, I'll go through kind of the basics. I've got students here, so I'm not afraid to put up math. But you'll recognize these as being fairly simple approximations to thin lens equations. So paraxial thin lenses, Abbe number is defined by index at 3 wavelengths within a band. So you'll have the center wavelength here and then 2 at the edge. And then you've got your classic achromatic criterion, so the ratio of the power in diopters over the Abbe number of the different lenses in the system. Those must all add up to 0 to be achromatic. To have a really good achromat that doesn't just correct at 1 or 2 wavelengths, but at 3, 4 wavelengths, you also need to worry about partial dispersion. And that is essentially the change of index over the first part of that band to the change of index over the whole band. So you can start to think about, maybe like a second derivative. And so here's partial dispersion in Abbe number that I mentioned earlier. And here you will be looking for things that fall along a horizontal line. And here I've got this yellow line. This is what we call the normal glass line. So this was noticed way back in the 1800s that most typical glasses fall along this line. It's for chemical reasons. And it took many, many years of experimenting by the guy that our company's named after, Otto Schott, to figure out how to get glasses that don't fall on that line and get you closer to a horizontal line. The first thing that was found was naturally occurring calcium fluoride, and then they had to go figure out why that worked and how to make glasses that sort of mimic that behavior, and you can see some of them there. So at any rate, we have this huge list. There's a couple of hundred actual optical glasses if you look at all the manufacturers. Huge pile of materials, lots of combinations of properties to choose from. And you go through and you sort through them, both for their optical properties, but also maybe thermal expansion, maybe price, maybe how easy it is to polish, those sorts of considerations. Pick them out, try them out nowadays in some software. Once upon a time, it was a bunch of ladies with pencils and abacuses, basically. But now we've got this lovely software that tells us how it works. And then on top of that, as I mentioned earlier, you have to consider thermo-optic effects. So here, it's essentially dNdt, change of index with temperature, over n minus 1 minus the thermal expansion of the material. That's all in ppm per K. And if you want to make a doublet, that's what you have to do. So this is, again, all fine and good, except for the fact that I'm going to need a whole pile of these if I'm going to be working in the infrared. So if we go back to first principles on this and say, well, what is refractive index? Well, typically, we've just been measuring sort of how the light is bent by a material, and we do that by looking at emission lines from lamps. And the reason that we use these particular wavelengths is because they were discovered to work fairly well back in the 1800s and be easy to reproduce. There's really no other reason than that. If we look at the fundamentals of the material, that's a different story. So here we have SiO2. This is going to be the refractive index and the absorption coefficient across a very wide span of frequencies. And you'll see these peaks in the refractive index. That's due to essentially oscillations of the different electrons or atoms in the material, the bond strengths, the weight of the atoms, et cetera, all figure into that. You can add all those different effects up, and you can calculate essentially what the index is at any wavelength or frequency. So this, then, therefore, is actually a fairly well-defined curve. We don't need to necessarily have all these different wavelengths. What we need to do is understand the curve. So well, let me skip that for a minute. So if we go ahead and look at how this curve is defined by these oscillations, we can simply just put these into fitting coefficients, for lack of a better word, just combining all those things like the reduced mass and so forth into handy coefficients, fit it, and we can then come up with an expression that will define the index at any wavelength in the range. And then what we can do is, if we want to have an idea of what dispersion is, let's not look at predefined differences between index at wavelengths. Let's just take the derivative. We've got this thing called calculus now. We can do this. So if you take the derivative of index with wavelengths, you get this expression here, and then you can derive essentially an instantaneous version of the Abbe number here. So this is just purely based on derivatives. And what you see, I put up a few of the glasses from our catalog here, is that they have essentially the same shape. The curve is always the same. It's just shifted around to different locations. So different wavelengths for the minimum and different values of the dispersion at the minimum. And so the only really important defining point on that whole curve, until you get into really small details, is the location of that minimum. So I plotted that here for all these different glasses. So you can see kind of how that maps out. The nice thing is that this kind of draws attention to the fact that the materials are really not different. They're actually quite similar. There's just subtle differences in their behavior, but for the most part, all optical materials are the same. The problem with infrared comes in that if you look at these curves, many of them cross. And so if you think about the concept of a crown glass versus a flint glass, what that means is I've got a high dispersion material and a low dispersion material. But now, that's all fine and good if I'm in this really narrow region here. But if I start to add in infrared, all of a sudden my crown is going to become a flint and my flint's going to become a crown. And instead of having good correction, I'm going to have horrible correction. So if I'm trying to fix a system that will work over a very wide range, I need to make sure that those lines never cross. And in fact, that they stay as parallel as possible with wavelength. So that's the real fundamental thing behind building a new glass map. We can also look at instantaneous partial dispersion. So as I mentioned a little bit ago, partial dispersion is basically the second derivative. Here you can see it derived. And you can also then derive an instantaneous partial dispersion, just like you do with an instantaneous Abbe number. And I took that figure you saw before with the minima on it, and I plotted it again here. And this time you see the instantaneous partial dispersions of the glass. And what, if you get into the details of it, eventually comes out at you is that materials with similar wavelengths for the minimum have similar partial dispersions at all wavelengths. And that means that it'll make a good doublet at all wavelengths. The other thing that means is that they'll never cross each other. And so you never have to worry about that inversion between a crown and a flint with different wavelengths. There's some other fine details in this. So for instance, on our glass map, you'll see things that are N-type glasses. That means they're lead-free. You'll see glasses that are not lead-free. And often they have the same name. For example, SF6 and NF6. While those do have the same properties only in the visible, and that's how that's defined, if we look in the infrared part and in the UV part, they're completely different. And they have different chemistries, so there's good reasons for that to be the case. But it's important to realize that when you try to get into broadband applications, that's part of why the simple glass map doesn't work, is because the fine details when you get out of that very narrow range in the visible can be quite different. So if we continue then, I mentioned earlier, you have this achromatic criterion, so it's the ratio of the power in diopters over the Abbe number. So then power in diopters is here. We have n minus 1 times the difference in the curvatures. We have the Abbe number, which is instantaneously defined here. So if you combine those together, you get this. So it's simply the sum of the derivative of the index over wavelength times the difference in the ratio of the difference in the curvatures. That has to add up to 0. So then this dn d lambda is really the defining characteristic of the glass. So it's not really Abbe number per se that tells you what's going on. It's just simply the derivative with respect to index. So if you pick some glasses now off of this list that I put together, and this is a very reduced list from the glass catalog, you can actually kind of use this to hone in on what might work. So in this case, as I mentioned earlier, you want glasses that have very similar minimum wavelengths. So I show two that are quite different. NFK51 is over here. F2 is over here. Wavelengths are quite different. And the correction is relatively poor. And as I choose a glass combination that's closer, I will get better and better performance. In this case, you can see NFK51 and NZK7. They're much closer. And I can even go as far as to split power between two different elements and kind of synthesize a third glass type that's an average of the two. Sorry, I don't know what it wants. Okay. So this is how you can start to use that glass map to build achromatic systems. So here is, when you put all the data together, the full glass map for all of the shot glasses. And it does look a little bit busy, but let me explain it. So in here we have color. Color is the thermal optic coefficient. We have the size of the dot. That's n minus 1. That tells you a little bit about how curved that lens is going to be and how much of a price you're going to pay in aberrations. And then you have the location of that dispersion minimum. And one of the interesting things as a chemist that comes out is that the glasses fall into families. And you can see those outlined here, different series. And they're chemically similar. So in this series 1, they're all lead silicates. So you're just simply moving essentially in the amount of lead that you have. In series 2, these are titanium-containing glasses. So you replace lead with titanium. That's the element that raises dispersion and index. And it has different properties, chemically speaking. So it does something different to the Sellmeier terms that define that dispersion relation. And so therefore, it moves the minimum. But again, you just slide along a line as you move in the amount of titanium. This series here is the lanthanum borates. So you have boron and lanthanum now, and lanthanum is the element that gives you your high index. And boron is the element that gives you what we call anomalous dispersion, or the ability to get off of that normal glass line. And then the last series here, these are high fluorine containing glasses. So fluorine pulls down the dispersion. The nice thing about this is that because these chemical series jump out at you, then me as a glass designer, if you come back to me and you say, hey, I need a glass that falls on a particular place of the map, say right here, I can go back into the lab and using a fairly basic knowledge of the chemistry that got this to happen, I can go and develop a glass specifically for your needs. That goes back to that idea of tailoring. So having something that's really based on fundamental material science rather than just sort of measurements that were ad hoc put together 100 years ago is very helpful, I think, in fostering that communication between the optical engineers and the material designers. So I'll get into a little bit of this idea of dispersion in anomalous glasses. This was somewhat mysterious for a long time. I think we can put the question of what makes dispersion anomalous in some glasses to bed. And I'll talk about that in a bit. So then if I go through and I pull out of that diagram, let me go back just a second. If I want to build an achromatic pair, all I do is I pick a crown glass, I draw a vertical line, and I pick a flint glass that falls near that vertical line. The farther up the line, the better in terms of difference in Abbe number, because that's what that gives you. But then you also have to keep things in mind about, like, what's the index of the glass, and is it going to be, maybe it's too refractive and I'm going to have crazy focal lengths or something like that. But you can pick a very small subset now to run through something like ZMAX or Code 5 or what have you to put into your design and see what looks good. So if I do that, I've now selected some, and you can see them chosen here. So here I've got NFK51. NKZFS4 and NLAK33A, and if you look at what people actually do in the literature or what people actually do in their designs, those combinations are very often chosen for different reasons, but nonetheless, that's the ones that are chosen. So it tells you that probably this actually does work. And indeed, if you look at this, this sum here that is our achromatic criterion, you can see that the correction is very, very good, even compared to our triplet that we did earlier without any real knowledge of the materials. And I show another one here too. This is PSF8. This is a lead glass, and LGSK2. It's a fluoride glass. This one would be really good if you're trying to get into the infrared applications because it has a much lower dispersion in the infrared. But at any rate, the point of this being that this can be now a tool to start kind of looking at how glasses might work in a more general sense for broadband applications. Yeah, let me keep going for a second. So the nice thing about this is, and this is an even busier chart now, but I'll take a few minutes to explain it. This is not defined for any predefined wavelengths. I can use any wavelength I want for this. All I need to do is have a Sellmeier equation to describe the index, and I can put it on a chart. So here I've got not every material known to man, but a pretty large cross-section going all the way from the UV out through the visible. So here you can see in this little area, these are all those optical glasses you saw in the visible before. So this is how full the glass map is for visible applications. And that's just the shot version. If you add in the other material makers, it's a very packed little space. And if you look at the other wavelength ranges, they're basically empty by comparison. But the same principles apply that I saw before. So if I draw vertical lines, I can pick out doublet possibilities. If I draw triangles, and this is what you would do on a normal glass map, you would try to draw a big triangle, you can get to good triplets. And as you move in this direction, you move from UV applications down through the infrared. Interestingly also, as you move in this direction, the atomic mass of your glass is increasing, so you can see some chemical trends here as well. And then you move in this direction, essentially you're getting tighter and tighter covalent bonding between the elements in the material. So again, chemistry comes into play. And again, if I get into understanding the chemistry in some of these materials, I can go back, and if you tell me you need a material that falls in a particular place, then I, as a materials person, can tell you which material will get you there. So I think, to me, this is a better way of looking at materials than just the standard old glass map. Some of these combinations that I list here for doing different broadband applications, you can go into the literature and find. They were achieved at by other means, but nonetheless, they found the same systems work. So again, that kind of suggests that this holds together in terms of a way of doing optical design. But in a minute, I'm going to get into how I can use this in the other direction, which is, I think, the more powerful tool. So how can I use this for finding new glasses for multispectral optics? So the concept of partial dispersion. How can I control partial dispersion? I want to move off of that normal glass line so I can get those well-matched pairs. Essentially, partial dispersion is controlled by the infrared side of that Sellmeier curve. So here I've shown the infrared portion of that complex index curve that you saw before for silica, and this is for water. And you can see they're quite different. Water has a much lighter element here with hydrogen. The reduced mass of that bond is much, much lower. Its frequency is higher, and that means that that oscillation moves to a shorter wavelength than the visible. That means that the interaction with photons that are at visible wavelengths is much stronger, and that essentially pulls down the index curve. You can see how different the index curve looks, the partial dispersion looks from the other materials. And what that means is that you have a much steeper curve in terms of dispersion, and the wavelength for the minimum moves much further out toward the visible. So that's a very, very anomalous material. The same thing works for boron. So boron versus silicon, and I mentioned that all the way back here, boron tends to be up here and to the left. Those are very anomalous glasses. I put water right here just for reference so you can see that it's indeed kind of at the anomalous end of things, and that's because the boron-oxygen bond is also very high frequency, very energetic. And so boron being in a glass pulls that refractive index curve in such a way that it makes it anomalous. That's just one example of how this works. let me go forward. There are some problems with using Sellmeier coefficients, and I've had some discussions with some other people who try to get into really heavy details of how I do fitting, of index curves, and how I can use that information. One of the things to keep in mind is that these are the actual data points from our catalog glasses, and I show on here with the blue line the wavelength for that minimum for the dispersion curve. And what you can see is that almost always that's very far out near the edge. So I have very little data to do that fitting from. So if I'm going to use Sellmeier coefficients as a way of sort of understanding what's going on chemically, I'm going to have serious problems because if there's any error in that measurement at all, I'm going to get completely the wrong number when I fit it. So there's a big issue with going back to look at Sellmeier dispersion curves that are in the literature because almost always they lack sufficient data out here in the infrared. And that is something that I've actually had to go through and try to address and done a lot of that in here. Another thing that I wanted to mention is the measurement precision. I've seen people with a lot of different formulas for dispersion where they try to get to 6, 7, 8 decimal places of precision. It's important to remember that those aren't really real because this is glass, so it's sand and rocks and seashells put in a hot thing. Okay, and that's kind of exaggerating a little bit because there's a lot of complexity in getting that to be exactly the same every time. But there's going to be variability from batch to batch, and we're doing things with six decimal places here, and there's not many materials that you would ever want to hold to those kind of precisions, but optical glasses are. And so you have to keep in mind that throwing too much precision into a design, and I mention that because I see it a lot from relatively new designers, throwing a lot of precision into a design isn't really manufacturable. And coming up with a model that requires that level of precision isn't really usable because at the end of the day, the material that you'll have in your hand won't match it. So you have to build some level of tolerance to imprecision in when you start to look at these things. The way we specify this is we have what we call steps for refractive index and Abbey number. You can see them defined here. And some of them are actually fairly big. So these are in ppm. So 50 ppms, 20 ppms, etc. So you're looking at usually variances in the 5th decimal place. Homogeneities, again, in the ppm level. And that can be very high. Homogeneity is relatively easy to do compared to exact reproduction of a refractive index every time. And so this is actually something that comes out of our literature of what you might expect from batch to batch for our refractive index variations to be. Most people, if they end up with a design that really needs a lot of precision, they will get the index for that particular melt or even that particular chunk of glass to make sure that they have it. So going to too high of a level of detail in your models doesn't really, I think, help too much. So in fact, we can reduce the complexity quite a bit. So here I've taken just a small subset of the measurements that show up in the optical glass catalog and said, okay, what if I reduce the number of measurements that I do? How much of a penalty will I pay in terms of precision? The blue line is the one that uses just this small subset of measurements. So relatively little penalty is paid. I have a lot of customers come to me and ask, hey, can I get 15 extra measurements of tiny steps of index made so that I know exactly what I'm dealing with? Trust me, you're just fine interpolating between the measurements that you have. You're better off spending money on getting measurements on that particular melt if you're really that worried about it. But I also get customers that say, hey, can I take the measurements that you have and extrapolate out a little bit past what I have here? No, absolutely not. Do not ever extrapolate data out. This very quickly goes into realms that are going to completely ruin your performance. So just to throw that out there, there are some levels of complexity, such as making sure you get all the way out as far into the infrared and into the UV as you can. You need those levels of complexity to make a robust design. So we can also simplify the Sellmeier itself, not only just the measurements, but also the equation. And the reason that we might want to do that is to make the fitting more reproducible, more repeatable, and give us something that we can actually use for modeling chemistry. So here you can see my proposed simplified Sellmeier equation. You remove a couple of terms here, you pull a square off because it's not really needed. You then simplify these derivatives, which is a little nicer to work with. And I go ahead and show the errors on the refitting of that data with this reduced Sellmeier. And all of these fitting errors are within step 1.1 in our catalog. So essentially, they're within what we can produce. So it's really not a performance issue to do this, especially if you're going to go in, if you have a really, really high need for precision, you're going to go in and measure that particular melt anyway. And the reason that I do that is to enable now really reproducible fitting. So here's what I do. I use this. This is the actual quantum mechanical description of this Sellmeier equation. So we've got oscillators in the UV and in the infrared, and we've got a DC dielectric constant, and that's it. And then I start to say, okay, what are the correlations between the different terms in the Sellmeier and the actual chemistry? And so here we can see I've outlined the glasses. There's a lot hidden in here because there's just so much data. But we can clearly see that those idea of families jump out again. That makes sense because the same chemistry should, in principle, lead to a similar dielectric constant. It should, in principle, lead to similar wavelengths of absorption in the infrared. It should lead to similar UV band gaps and so forth. So one would expect to find these families and be surprised if you didn't find them. The same thing happens between the UV and the near-infrared, though the UV is actually relatively easy to understand. The infrared gets a little bit more complex, and that's because subtle changes now in the chemistry have some larger impacts. We can also look at the oscillator strength versus the frequency for the oscillator, and you can again see families clearly jump out at you here. Oh, I'm sorry, maybe. Let me. Sure. So you can see that both, again, in the visible and in the infrared. They're very strongly correlated, and in fact, it's actually relatively easy to predict what these are going to be if you understand the chemistry of the melts, and that's where things start to get proprietary. But again, this allows us to sort of foster that dialogue between the optical designers and the material makers. And again, we get back to the idea, and we see it now clearly in some of these, why boron is so important in describing the instantaneous dispersion and the impact on the anomalous behavior for some of these classes. And then you can get into, here we actually look at, this is the departure from the normal glass line. And you can start to see now, again, how families pop up. And sure enough, the departure is very strongly dependent on the boron content, which is what is in these LAs and so forth. Whereas these guys are fluorine and are pulled the other way in terms of their partial dispersion. All this is to say that we can then actually build a model. And here we have the outcome of that model. So fitting things like Abbe number, partial dispersion, this departure. I can put together a model that will predict an Abbe number, predict a partial dispersion, and hit that very, very close just on first principles from chemistry. So then, like I said before, if you have a combination of properties that you need to do for your particular optical design, you can come to us and say, hey, this is what I need. Can you engineer a glass that will put me just exactly here? And unless it's some crazy combination, probably the answer will be yes. And the same principles work not only in the visible, but also in the infrared. So just to kind of sum up, and I know it's a lot, and please feel free to go to town with questions. I think that looking at these things from these terms of instantaneous dispersion really do kind of foster a better understanding of what's going on with these optical materials. It's not just numbers in a table and I just looked them up, but actually what's going on with the optics as a function of wavelength, and how is that going to impact what's happening with the light in my system. The minimum dispersion wavelength represents essentially your partial dispersion, and the Abbe number, instantaneous Abbe number, gives you your dispersion. So essentially, low dispersion glasses will be near the bottom, high dispersion glasses near the top, and infrared materials will be farther to the right, UV materials farther to the left. So it's relatively easy to see what materials might work for your application. We can use that to build this idea of a universal glass map, and I think that really comes to show its power when we're looking at multispectral, and as time goes on, I see more and more of that. I wouldn't be surprised if you in your careers also started to see more and more of that idea come up. certainly more chunks of the spectral range, and this can work all the way from gamma through radio. You really only need to know the dielectric constant of your material versus frequency. And again, you can very quickly kind of get an idea in your head of how that material behaves dispersively. And for me, as a materials person, the really powerful thing for me is being able to then go back and engineer a particular optical material. And this is why I love glass so much, because I can do that there and I can't do it in anything else. As long as you've got a robust fitting procedure so that you can understand what's going on with these Sellmeier terms and what the chemistry is doing, you can then go back and look at the compositions and how those impact the Sellmeier constants. And then we can start to have discussions about, like, well, can you make me the same glass but that's cheaper? Or maybe one that performs the same but polishes better? Or maybe one that's lighter because I need to save weight? Or whatever. We can actually get into some of those discussions. And again, I think that starting to have those discussions a little more actively between the optical designers and the material people would be a very big thing for the industry as a whole. So I'll just, I guess, leave it there, and please fire away if you've got any questions.
Plenty of time for
questions. I warned you I was fast.